Hello, and welcome to Things You Thought You Didn't Need to Care About That Have a Big Impact on Your Job. Every time I say this title aloud, I'm reminded that naming is the hardest problem in computer science and every other field as well. What I'm really going to be talking about today is the invisible forces that are shaping your job, the things that, weren't on the computer science curriculum, but actually affect how we do our work. They affect everything about our work. And a lot of these really have then to do with maybe the other subjects that we did in university and forgot, or the subjects that we didn't even go anywhere near. And what they then affect is some of the really big questions. So let's start with the biggest question of all. Why is everything hard? Why are computers terrible? Why can't we have nice things? We do get slightly more cheerful after this, I promise. So the answer to this, there's obviously a bunch of reasons for this, but one of the answers to this has to do with geography. It turns out that many of us computer people missed an important lesson. And that lesson is that there's a country called Norway. And because Norway exists, and because the Norwegians made some very poor choices about naming their country, they ruined things for the rest of us. Who here knows where I'm going already? A couple of hands, yeah. So let's look at some YAML. YAML is already a mistake anyway, but we have YAML, so. And if I wanted to make some YAML to define, say, ski regions, I might do something like this. And I've got a nice little list. And then what happens is that this YAML gets parsed into the native format of whatever computer language I'm using. So the parsing might go something like this. Here I've got it turning into JSON. But I get a nice little array. So I've got France, I've got Switzerland, I've got Sweden, and then it all goes horribly, horribly wrong. See, it's all the fault of the Norwegians, because this nice little parsing that turned no into a Boolean meant that all of a sudden, instead of having a ski region, I just have total failure. So the thing that makes me really sad about this is that, it's easy to laugh at YAML, and YAML maybe did make some bad decisions, but I think any of us might have made a similar decision and said, let's be really friendly, and let's try and be flexible with our types, and let's sort of try and parse things out. And this totally reasonable decision had a bad outcome, particularly if you live in Norway. So how can we avoid this in future? How can we try and understand the consequences of our decisions, given that the world is pretty complex and it includes these unexpected entities like Norway? Well, the answer to this, I think, is systems thinking. Systems thinking is really good. I would recommend everybody to try and read up and practice systems thinking, but systems thinking also has a problem, which is that it's kind of by definition, you have to spend a lot of time doing it. And kind of by definition, it ends up being complex itself. And I don't want complexity. I'm moving in a fast-paced world. I need to make decisions fast. So sometimes systems thinking is the answer. Sometimes I need something more reductionist. Sometimes I just need to turn a situation into a number so that I can use that number to guide my decision. And this is where statistics come in. Now, this is really unfortunate for me because I did do statistics in university. I didn't like it at all. It didn't make any sense to me. That has had some sort of bad consequences for the rest of my life because this actually comes back to geography again. What do you call a statistician who lives in San Francisco? Because there is such a concentration of tech employment and tech money in San Francisco. If you are a statistician who lives in San Francisco, you are not a statistician. You are a data scientist, and you are making a ton of money. And this is because the thing that is taking over the whole world, and certainly the thing that is taking our whole industry now, is really fundamentally founded on statistics. And from statistics, we got data science with, sort of a bump in salary. And then from data science, we got machine learning with another bump in salary. And then eventually we got to this sort of AI behemoth with absolutely incomprehensible salaries. And this is bad because it means we're not earning those salaries if we're not doing AI. But the really, really bad thing is that even if you don't want the AI money, you still kind of need to know statistics. Statistics is still really important and useful. And I'm not going to give a whole statistics course because I don't think I could fit it into the 44 minutes I have remaining. But I just want to talk about one area of statistics which I didn't know about until recently, which is pretty useful. And this is Bayes' theorem. Bayes was a priest who lived in the 1700s, and apparently God didn't take up very much of his time, and so he had lots of time to do mathematics instead. And so he came up with this formula, which is now used in almost every area. And I mean, it's used for all sorts of things, but I want to give an example that's quite close to what we do with computers and what we do with email, which is spam detection. Most modern email spam detectors are Bayesian. So if I want to write a spam detector, what I really want to do is I want to detect the spamicity of the email. This isn't a word I just made up. This is actually what it's called. So if you want to sound like you know about spam, you can talk about spamicity. So let's take a typical spam email of, exciting offer just for you, deep discounts on Viagra, limited time, act now. This has been sort of a typical spam for a long time. It's 2025. Spam actually probably looks a bit more, so instead of talking about Viagra, maybe it's going to talk about Ozempic instead. So this email is pretty clearly spam. I can flag it as spam if I just look for that word. But spammers are not stupid. They do not want to get caught by the spam filters. So instead of saying Ozempic spelled like that, they will vary the spelling. So I can ban the word Ozempic. I've written my spam filter. And then what happens is they change it to a different spelling. So they change it to that. To a human, it still reads exactly the same, but it slips through the spam filter. Nothing in there is flagged as spam. So let's try again. I'm going to extend my banned word list. So I've got Ozempic, and then 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 I've got Ozempic and Ozempic. And this is a pretty futile task, right? Because any variation I can come up with, the spam filter, the spammers can come up with another one. For example, there's two versions of O, a Greek O and a normal O, that look exactly the same, and they're different. So this can just go on forever. And it's pretty stupid, ultimately. So can we do better? I think we can, because as a human, when you looked at that email, part of what made you realize it was spam was the word Ozempic, but it's also about what's not in the email. Because if you compare this to an email that a person might actually write about Ozempic, because people do talk about this by emails, you might say something like, hey, Alice, are you still good for next week? We had drama because the dog threw up in the dishwasher. Luckily, it was easy to clean the dishes. I've started Ozempic, and, I can see it's affecting my appetite, and there's a whole bunch of other stuff. So clearly, in the spam email, there are those problematic words. Ozempic is very suspicious. Offer's pretty suspicious as well. But if I look at the good email, the ham email, there's some words there that almost never appear in spam. For example, yesterday happens to not appear in spam very often. It's just not one of those spammy words. Dishwasher never appears in spam. For some reason, I never get spam offering me dishwashers. I don't know why. So I can make, instead of just making one pile, which is the spam words, which is just a hopeless task, I can make two piles. I can make a pile of spam words, and then I can also make a pile of ham words. I should say as well, ham I didn't make up. This is actually the opposite of spam is ham if you are a spam scientist. So with these two piles, I can then go and some of the words are just like they're going to appear in both lists. But there's some words that are pretty distinctively more likely to be spam, and some words that are more likely to be ham. So I can take those words and I can put them in the bags. And then with that, I can now start doing some analysis. So what I really want is I want a probability. So Stephen Hawking said, when he was working on A Brief History of Time, that for every equation he put in the book, he reckoned his sales halved. And I think it's probably the same for conference talks, right? Like for every equation I put in the talk, my speaker ratings halve. So I would encourage you to go rate the speakers. It's very helpful, but maybe actually don't rate the speakers because I've got a lot of equations coming up. So what I want is this is probability notation. So I want the probability of spam given that this email has the word Ozempic in it. And this is Bayes' equation. So you can see it's just a big mess of A's and B's. So what it says is I want the probability of A given B. And in order to do that, I can calculate that from the probability of B given A times the probability of A divided by the probability of B. And so with this, I now have my guidance for a decision. So I can substitute that in for my Ozempic problem. So what I want is I want the probability an email is spam, given it says Ozempic, and I can calculate that by knowing what proportion of spam talks about Ozempic times what proportion of email is spam, divided by what proportion of emails in general talk about Ozempic. And I can just sort of make up some numbers here. So let's say 1% of emails of spam talks about Ozempic, and that proportion of emails, 0.001, talks about Ozempic, and maybe let's say 6% of emails through the whole system are spam. And with that, I can then come up with a 60% probability. And of course, I can iterate. So I'm not just going to look at that one word. For every email, I'm going to then feed that into that equation and recurse. So let's go back and look at this equation, because you'll notice I just put a whole bunch of numbers in and told you that that gave me a 60% probability. But there's some problems here. What if I don't know any of those numbers? And what if I don't know that number? How do I make progress? One of the magic things about doing things in a Bayesian way is that you are allowed to guess. So although this seems like the most useless formula ever, I can just guess. Or for the denominator, if I'm just trying to do a comparison, I can just ignore it. But there's another problem with this equation, which is sort of not a practical problem, but a philosophical question, which is you can see this is just a mess of A's and B's. So I want to calculate some probability to do with A and B. And in order to calculate that probability, I need to know everything about A and B. But if I already knew everything about A and B, I probably wouldn't need to be calculating this probability. If I knew what proportion of all emails were spam, I'd be in really good shape. I wouldn't be worrying about doing this one calculation. And this formula is fundamentally recursive. In order to know the probability of A, I have to know the probability of A, but I don't know the probability of A, and that's why I'm doing the formula. And it just all becomes a little bit complicated. And so this recursion, some people get really upset by this, particularly the statisticians, and they say, it is totally cheating to do a formula where you put the same information on both sides. That is just cheating. The computer scientists here say, no, that is not cheating. That is a well-established technique. I am not cheating. I am just doing iteration. I am recursively iterating in order to improve my quality. We get really excited about tabs versus spaces. It turns out that the statisticians get really excited about this question about whether Bayes is a good way of doing things and whether recursion is OK when you're doing statisticians. So if you remember some of your emails that you sent to your colleagues about tabs versus spaces, they go way better. So one statistician, he sort of wrote this big essay, and he said that doing things with Bayes is just ignorance coined into science. You don't know anything, and you just throw a bunch of numbers around and then pretend that it's science. Someone else said, it is a staggering falsity. And I like this one, perhaps the only error to which the mathematical world has so deeply committed itself. So basically, everything is wrong, and anybody who does this is terrible, sort of. But the thing is, despite the fact that a lot of statisticians get really, really upset about Bayes, it's incredibly useful for all sorts of things. So let's take another example, not from computers. Let's say your friend comes to you, but your friend has a problem, which is that they are covered in spots. You have to diagnose your friend. So, what's wrong with your friend? It could be cowpox, or it could be chickenpox. Incidentally, does anybody know what you catch cowpox from? Someone said cows. That is a totally reasonable suggestion. Someone said chicken. It is not chickens. It turns out, in the modern era, what you're most likely to catch cowpox from is cats. Go figure. Historically, like in the 1700s, if you caught cowpox, you caught it from cows. Now it's cats. Does anybody know what you catch chickenpox from? Someone said chickens. It is not chickens. Weirdly, chickens was never involved. It's just called chickenpox because you look kind of like you got attacked by a chicken after you're covered in spots. Naming is the hardest problem. So let's do the math here. So let's assume, so we have that formula again with just spots, spots, spots. And let's put in some numbers. So let's say 85% of the time when you have chickenpox, you get spots. Sometimes you don't. This happened to my child. Let's say 1% of the population have chickenpox. We will just ignore that denominator because it's the same in both. Let's say for cowpox, actually, you're more likely to come out in spots. It's a bit more spotty. So you have a 90% chance of coming out in spots. But of course, cowpox is pretty rare. Like, I've never met anybody with cowpox. Nobody has ever met anybody with cowpox. So let's say it's like 0.0001% of the population have cowpox. So we can put those numbers in, and we can say that it's a 0.85 on that one and 0.0009 on that one. In other words, the probability of chickenpox is way more than the probability of cowpox, and we can tell our friend it's chickenpox. Now, at this point, you're sitting here going, why did I need that really fancy formula in order to tell me what is totally obvious, which is that my friend is more likely to have chickenpox than cowpox? Duh. So what's interesting about this is that although, like in this formula, the answer is totally common sense, sometimes when you apply Bayes' formula, the answer really isn't common sense at all. So let's take another example. I have invented a magic static analysis tool. It's 99% accurate. So that means the rate of false positives is 1%, and the rate of false negatives is 1%. So I run my static analysis tool against code, and it gives a check mark, and it says the code is clean. What's the probability that the code is clean? I'm waiting for someone to say 99%. Someone said 98. Trying to be clever, but it's sort of close. So the chance that the code is clean depends a lot on the code. And so if I give you some extra information and I say, I run my static analysis tool against the code, and it says that the code is clean, but the code was not Java code. The code was C code. What's the chance that the code is clean? So, as we all know, C code, pretty much all C code, either has some kind of memory leak from home-rolled garbage collection or some kind of memory overrun, buffer overflow disaster, or some pointer error or something. So let's assume that we have to look at the probability of clean code given, for C code. So our accuracy is 99%, but then, so we'll just fill in that denominator. The denominator kind of ends up being a bit recursive to calculate too, so just trust me that the denominator is 2% here. And then let's say that only 1% of C code is free of errors, which I think is actually generous. And that's why we have Rust, of course. So with those numbers, what that means is that even if my 99% accurate tool says that this C code is free of errors, there's actually only a 50% chance of errors because the probability of errors is so high that that 99% turns into 50%. And you can use sort of similar reasoning with medical diagnostic tests, actually. So sometimes a medical test that is very accurate, if it's looking for something that has a really low rate of occurrence in the population, will give you way more false positives than actual useful results. So it sort of ends up being really difficult to try and decide how to interpret medical results and what tests to fund. And I find this so interesting because it is so totally not common sense that I go to you and I say my tool that has a 99% chance of being correct only has a 50% chance of being correct. And it's like, well, which is it? Is it 99%? Is it 50%? And the answer is, it depends. We could be architects. But Bayes is everywhere. It is so I mentioned, you know, a lot of statistical work uses it, a lot of machine learning uses it. So for example, you know, your classic sort of discriminator tooling is going to use some sort of Bayesian analysis to decide if it's a chihuahua or a blueberry muffin. Medical testing uses it to try and give some more information on how you should interpret test results. It's everywhere. So how should you use Bayes? What I would recommend is, you know, you may find that it's actually useful to use the Bayes math in your day job, but even if you don't, you can still take advantage of this to do better at work, which is instead of telling your boss, we have no idea, you can say, we are adopting Bayesian thinking, and you sound like you know what you're doing. You sound like you're doing something really clever when actually you just have no idea. So let me switch topics a bit from statistics, which I did in university and found really hard and didn't like, to concurrency, which I did in university and found really hard and didn't like. Concurrency is really hard. It makes my head hurt. It makes a lot of people's heads hurt. Fundamentally, concurrency is hard for two reasons. One is, as soon as you start writing concurrent code, you know, it's a bit like the C code, right? Your chance of errors just goes up a lot. But then the other problem with concurrency is that even if you write error-free code, you may actually not get the benefits that you were hoping for. You have to do a really good job with concurrency in order to have it working for you. And there's limits on how good a job you can do. Now, before I go to the next slide, I should say that the last time I gave this talk, not one, but two people came up to me afterwards and said that my section on concurrency was all wrong, to which I said, of course my section on concurrency was all wrong. I explained that I found it really hard. Weren't you paying attention? Duh. But they didn't seem happy with that. So I should say concurrency and parallelism are distinct. But it turns out if you go to the internet and you look up the difference between concurrency and parallelism, you can find at least 4 authoritative answers that say completely different things. So some people will say concurrency and parallelism are the same thing. I'm kind of using them that way here. It's not right, but it's convenient. Some people will say parallelism is a subset of concurrency. Some people will say that concurrency is a software concern and parallelism is a hardware concern. And some people will say that they are completely distinct. So I figure you can choose the definition that's most convenient for you. Here I have chosen the definition where I'm kind of treating them sort of the same. So switching to parallelism for this, Amdahl's law is really interesting and really depressing because what Amdahl's law says is if you are writing parallel code that you are hoping will execute in parallel, but of course you have to have some coordination, otherwise it's not a system, it's not an application, it's just a whole bunch of completely disconnected programs. The amount of time that your code comes back to coordinate with the rest of the application really, really limits the speed up that you can get. So you can see here, if my code is 50% parallel, there is no point running it on more than 2 cores because I'm never going to get that speed up. Even if I write the most amazing concurrent parallel code and I get to like 95% parallel, I'm still not going to get any benefit if I go past about 20 cores. And so this is fundamentally depressing, because it means you can work really hard, you can fight all of those concurrency bugs, and you're still going to get, you know, like a 4 times speed up if you manage to get 75% parallel. And so then this comes back to concurrency makes my head hurt, because, you know, I tried to do a really good job and I still didn't get that much of a benefit. But there's another reason why concurrency makes your head hurt, which we can go back to Bayes. Because let's look at this. So if I have a headache, can I blame concurrency for my headache? Concurrent, and so then, in order to work that out, what I need to know is how many devs can cope with concurrency? What's the proportion of developers who, when given concurrency, have a headache? What's the probability of concurrency? And also just what's the probability of headaches in the population? And in this equation, that probability of concurrency is changing. And the reason for this, going back to school again, is electrical engineering. Because it used to be, if you were an electrical engineer and you were doing chip design and you wanted to make it go faster, you could just pack more transistors onto the same core. It was great. And Moore's law said that every 18 months, the number of transistors you could pack in would double, and you could just continue making faster and faster computers. But then at some point, Moore's law kind of capped out. And in order to get more power on your computers, you had to add more cores. So in 2000, a state-of-the-art computer had 1 core. And then it went to 2 cores, which was massively exciting. Now, a state-of-the-art computer has, you know, almost 48 cores. And, you know, now we're sort of going up to, like, 128 cores. The number of cores is going up and up and up. And so what that means is the probability of concurrency is going up and up. If you want to actually take advantage of the power that is on your hardware, you have to be doing parallelism, and so you have to be doing concurrency. So why is this happening? It's because that single processor performance has plateaued. And so what that means is that as an industry, the hardware people are giving us parallelism. We have to be able to take advantage of it. And as an industry, traditionally, we're not very good at concurrency. It makes our head hurt. It's hard. Amdahl's law means that even if we try and do it right, we still don't really get much benefit of it. We have to do better. The good news, I would say, is that although we have to do better, not all of us have to do better. There are frameworks that can help. So for me, I work for Quarkus. A lot of my colleagues are really, really good at concurrency. I am not one of the Quarkus people who is good at concurrency, but a lot of them have come from a reactive background. A lot of them have come from a distributed background, and they are good at concurrency. They do not get the headache that I get. And I think what this means is actually the Quarkus team has made some mistakes in how we talk about concurrency to the rest of the world. Georgios and Guillaume talked about this morning as well, that when we first started talking about Quarkus and, you know, making the sort of the Quarkus website, what we said was unifies imperative and reactive, because a lot of them had come from a reactive background, and traditionally, if you were doing reactive, you couldn't do imperative, and we had this programming model that allowed you to mix both in the same application. It was really clever. It was really cool. We thought this was incredibly exciting, so we put it big, big, big on our website, and everybody looked at the website and said, but I don't want to do reactive programming because concurrency gives me a headache. So maybe Quarkus isn't for me. People thought they had to do reactive programming because we talked about it so much. So we've changed how we talk about it. You still totally can do reactive programming with Quarkus if you want to. All the capability is still there, but we don't put it as the first thing on our website. Instead, what we say is reactive core. So Quarkus is incredibly performant, it's incredibly resource efficient, it can achieve throughput and scalability that the alternatives can't. But that's and that's sort of, you know, there's all sorts of reasons technically why that is the case, but one of the big ones is that the underlying architecture, the core, is reactive. But the thing is, you don't have to use it unless you want to. So when you're thinking about, you know, in the modern multi-core world, how do I choose hardware? probably you want to have this fast reactive core wherever you get it. I would suggest Quarkus, because but then in terms of the user code, you could just do your normal imperative code, and you're going to get an advantage of it. Or you could do reactive programming if you're one of the people who really likes reactive programming. If, like the rest of us, you're not, you could do virtual threads, and then that will be sort of taking advantage of that reactive core. Or if you're using Java 25, you can use things like structured concurrency. So I mentioned virtual threads. Virtual threads have been coming for a long time. I think we're now at the stage where a lot of the libraries have sorted out the issues that they had with virtual threads, and the JVM has sorted out some of the issues that it had with libraries. So it used to be that quite a lot of code would end up pinning the thread. So even though you thought you were using virtual threads, actually you were all just running on one thread and your performance was terrible. That's mostly solved now. So if you're using Quarkus, you can add an @run on virtual thread annotation to any method. There's a reason that we don't have it as the default, which is that virtual threads are really cool. They give such a nice programming model and user experience. They still do have an overhead. So if you're doing something with lots of async I/O, definitely use run on virtual thread or an alternative. But if you're just doing normal code, actually you don't want to be running on virtual threads because it will slow you down. It is not a magic go faster feature, even though the name kind of implies that the virtual thread is like running off in the ether and it's magic compute. It is not. Now, when I started reading about virtual threads, I was really confused because this isn't the first time round that the JVM has tried a feature like this. Many years ago, the JVM had a feature called green threads. Who here has heard of green threads? A couple of hands. Most of you haven't. And the reason most of you haven't isn't because you're not paying attention. It's because green threads was a total failure. Green threads sort of appeared and then it disappeared. Why did green threads not win when run on virtual thread was exciting? I can see an answer. Yeah, go.
I think because they didn't use real threads to parallelize.
There was a very technical answer from the front, which is that they didn't use real threads to parallelize. I think that probably is part of it, but I would argue there's another reason as well, which is we just didn't need it. Although we were doing async I/O, because parallelism and concurrency are not the same thing, and you can do concurrency just with one core. Now that we're in this world here, we have such a strong need for that parallelism and that concurrency that we now need it to be in our programming models in the way that we didn't used to. Plus, as you said, the implementation is just better. And there was sort of a similar kind of cycle where it kind of didn't quite happen and then it happened with AOT. So when I first started working on Java, AOT was the big thing, and people kept asking, why can't I have AOT? And the answer was, well, you kind of have. We've implemented it, but you don't want it. Now, people really do want it. Why is it different? The answer is actually to do with meteorology, and in particular, clouds. Back when we tried to do AOT the first time, nobody had the cloud. It didn't really matter if your application started up quickly because it was running in a server room and you started it up every 6 months. Now we have these ephemeral instances running in containers, so we need them to go up and down much more quickly than we used to. But I mean, so we've had these sort of like mini hype cycles. So like if you came to Devoxx a couple of years ago, there were so many talks on virtual threads. And there still is such a lot of justified excitement about GraalVM. And then we have these sort of bigger hype cycles too. So like if you came to Devoxx in like 2017 or so and you went round the vendors, every single vendor would tell you that their solution was cloud native. Now, of course, every single vendor will tell you that their solution is AI. And the answer to this, I think, has to do with business studies. And in particular, it has to do with how venture capital works. Because if I am an investor, and I have a little bit of money that I wish to invest. What I might do is I might fund a baby company. And what I hope is going to happen is that that baby company will go through some funding rounds. And in each funding round, it attracts a bit more investment. And then it does the next funding round, more investment comes in, and then it does the next funding round, and more investment comes in, and then the next funding round. And eventually, what I get to is I get to what's called an exit. And that is where a lot of money comes in. So every investor wants to be getting to that exit. And so the exit, it might be an IPO, it might be an acquisition. But in all cases, the distinctive feature of the exit is that as an investor, as a founder, this company is no longer my concern. The company kind of goes away. It either becomes the shareholders or it gets absorbed into another company. But what I can do is I can just take my cash and I can go to the bank. So what kind of things make a company progress through these funding rounds until it can eventually get to the exit? There's a lot of really good things for companies to have. So for example, a company should be stable. Does this attract investment? Nuh-uh. A company should be profitable. Does this attract investment? Nuh-uh. A company should have revenue. Does this attract investment? Nuh-uh, not so much. What attracts investment is growth. What attracts investment is excitement. And so as an investor, what you want to be doing is you want to be optimizing for this growth and this excitement rather than the other things, because the growth and the excitement are what allow you to sell your stake at a profit. And Meredith Whittaker, who some of you may know from, because she's the president of Signal, she got asked this really interesting question. The question, they asked her, what technology do you think is most overhyped? And she said, it's not that any one technology is overhyped, it's that hype is a necessary ingredient of the tech ecosystem because of the need to progress through these funding rounds and then eventually get to your exit. And so you have to be generating the hype. So what are the implications of this? One of them is on the employment market. So a lot of people are finding it very hard to find jobs now. Even those who do have jobs are maybe finding it hard to move between jobs in the way that they used to. And this isn't just your imagination. It's not just anecdotal. You can absolutely see it in the job data. So this is the US job data. I know we're a super international audience. I don't have it for every country, but I do have it for the UK, where I'm living. And you can see, it's a smaller curve, but there still is that curve. What's going on? So this has to do with, partly with the hype cycle, but it also has to do with macroeconomics. Because recently, we've been in what's known as a ZIRP, a zero interest rate period or zero interest rate phenomenon. You would think zero interest rate means that the interest rate is zero. The clue's sort of in the name. That's not actually what zero interest rate means. What zero interest rate means is less than 1%. That's kind of like close enough to zero, we'll take it. And if you look at recent interest rates, since about 2010, the interest rate sort of dropped a lot to try and avert the subprime crisis. And then it sort of stayed really low. And then it started to creep up again. And then COVID happened. And so then it went way down to rescue the economy during COVID. And then just recently, so it went really almost to zero. And then just recently, we had sort of inflation and shortages and war and various horsemen of the apocalypse. And the interest rates sort of went way up. And so for a lot of this, for our whole adult lives, interest rates have been really close to zero. And so this recent spike was a big shock, and it seemed really unexpected. But if you look at a bigger period of history, what's actually unexpected and weird is that low period, because for almost the rest of, since we've been recording, we've had these really high interest rates. And that affects how people invest. Because in this sort of cycle where, we go through the funding rounds, of course, it's not guaranteed as an investor that you get to the end, right? It could be that actually you don't get those later funding rounds. And instead, sort of in one of the middle funding rounds, what happens is that instead of progressing, your little baby startup goes up in flames, which is rather sad, because what happens then is that all your money goes up in flames. But there is risk in this kind of investment. So if I have a pot of cash and I want to decide what to do with it, I could put it in a software company, or I could put it in something like government bonds. A software company, it has this really high risk, but then it's got this potentially really high return. A government bond, very safe, if you choose the right government. But, you know, the return, if you're in a zero interest rate period, is basically zero. So your money is just wasted. It's not working for you at all in that case. So the sensible place to put your money is the high-risk software company. What if, on the other hand, we're not in a zero interest rate period? What if we're in the post-ZIRP period? In this case, the interest rate is 4%. So actually, my money's going to be working for me for almost no risk if I put it in a government bond. So those software companies that I had been pouring cash into suddenly look a lot less attractive. And so software companies in general are getting less investment. With less investment, there's less hiring, and so fewer jobs. But of course, some of you will be thinking, wait a minute, I know what's causing the job problems, and it's not interest rates, it's AI. I haven't mentioned AI yet. Is AI killing jobs? Well, it's sort of interesting. Because definitely, sort of looking at that cycle, for some companies that are focused on AI, going back to the hype, AI is attracting a lot of investment. And in fact, those companies that are doing AI are attracting so much investment that it's then starting to create this kind of interesting macroeconomic environment where there's too much risk concentrated in just a small section of the IT sector. And I think an interesting thing about AI and the job market is a lot of investment is going to just the companies that are saying they're doing AI. And for a lot of those companies, but also for other companies, we're seeing these rounds of layoffs. And I think one of the things that's driving these layoffs, this is just a theory, is that if you are a company, you need to show that you're able to take advantage of AI. What's AI supposed to do? AI is supposed to replace your workforce. How do you show the investors, how do you show the market that you are taking advantage of AI? You have to show that AI has replaced your employees. How do you show that AI has replaced your employees? You get rid of your employees, whether AI has actually replaced them or not. And so I think some of the current layoffs are driven by this need to create a perception that AI is working. And then companies are sort of hoping that they can then catch up afterwards. But there's another really interesting thing about AI, which is that although we've kind of been promised that AI will make jobs go away, is AI going to make software jobs go away? I don't think it is. And this comes down to something that we can learn from economics called Jevons paradox. Actually, it might be Jevons paradox, I can never remember. In any case, this is something that economics, they just treat it as axiomatic, and they're always surprised that every other field has to keep rediscovering it. And I like to think of this as the highway paradox, because if I'm going to widen roads, well, so what Jevons paradox says is that efficiency improvements can lead to increased consumption. That's kind of surprising, that's why it's a paradox. So if I'm going to widen roads, what I imagine is that I'm going to have the same number of cars on these really wide roads, and it's going to be heaven for motorists. But of course, you all know what actually happens, right? It's this. I widen the roads, and I get 10 times more cars, and it takes me exactly as long to get from A to B as it did before. Depressing. This is why economics is called the dismal sciences, because they, have depressing truths like this. And so we're kind of seeing a little bit of this with AI and jobs now, because there was this really interesting study that they looked at professions that were exposed to AI and professions that weren't exposed to AI. And they found a paradox, Jevons paradox, which is that the professions that were exposed to AI were working more. They were working 3 more hours per week than they were before AI. What was going on? And their theory was that because if you were AI assisted, you were far more productive. If you were far more productive, there was so much more incentive for you to work that you then worked more. So it was kind of this, it's a paradox, right? That your time is so valuable that you have to work more in order to leverage the fact that your time is more valuable when all you wanted to do is just crawl under the duvet because it's a duvet. And I think, this is true. They weren't looking at software in particular. They were looking at all industries, but especially for software. Software as an industry is really not going away. And you can see this by comparing it to some other industries that have been disrupted by technology. So there's lots of these, of course, but I want to choose a slightly older one. In the 1800s, there was a profession called a knocker-up. And what a knocker-up was a human alarm clock. And the reason was because factories were introduced. If you had a factory job, you had to turn up at whatever time, 7 a.m. or whatever, on the dot. But you didn't have an alarm clock because they weren't going to be invented for another 160 years. How do you get up to get to your job on time so that you don't get fired? What do? You need someone to wake you up, so you need a knocker-up. The knocker-up as a profession actually continued until pretty recently. So until the 1940s, there were still professional knocker-ups. In the north of England, it continued till the 1970s. But ultimately, of course, this industry had to go away because there is finite demand. You can't have like infinite wakings up because only people who have these kind of factory jobs need waking up. People with like small children, they don't need waking up because the children wakes them. And as well, there's sort of some things you have and then you just want more. You have a chocolate bar and then you want another chocolate bar. But nobody ever says, I got woken up this morning. I liked it so much. I think I'm going to get woken up 3 more times today, right? 1 is the maximum per day that you could possibly want this service. So it went away. But with software, it's really different because the more software we have, the more we want. And so obviously we need software to do stuff, and then we need software to do more stuff. And then we need software to tell people about the software, and then you need software to bypass the advertisements in the software. And then you need software to bypass the software so that the ads still show. And then you need software to gamify software. And then you need software to monitor the software. And then you need software to debug the vibe-coded software because oops. And then you need software to manage the software. And then you need software to write the software. And then you need software to manage the software that writes the software because oops. And then you need software to try and avoid Skynet because oops. And then you need software to work out the meaning of life. And it just goes on and on and on. And you can see this in the data, because if you look at the number of software developer jobs, every time we've had an increase in productivity, an increase in abstraction, we went from assembler to high-level languages. Everything was so easy. We could write programs 10 times quicker. Did we have fewer software developers? No, we had more software developers. And I think it's going to continue. So we have this exponential curve. Maybe it will not be exponential anymore, but I don't think it's going to reverse and go down that U. So looking again at this job data that was really depressing, and you want to say, oh, it's because of AI. But actually, ChatGPT was introduced when that curve was already on its downward slope. And you can see it actually kind of stabilized after ChatGPT. So I definitely don't think we can blame AI for the job market, which I think is probably a happy note to end on, since I've covered all sorts of stuff. So to wrap up, statistics is important, even though it's annoying. Bayes is particularly useful. To achieve more power, computers have to add more cores, which is annoying because it means we have to do concurrency. Software is not very good at taking advantage of these cores, but we're getting better. In terms of our jobs, the rise of interest rates has led to a tougher job market for all of us. But I think this is a macroeconomic phenomenon and not related to AI, because Jevons paradox means that demand for software will go up even if AI makes producing software cheaper. So I can see a few of you with taking photos. I do have the slides here, so this is the photo to take, and then you can go and you can get all of the slides, because I know I've covered about 1,600 things and you're still catching up. And so with that, again, please do rate the session. Super helpful to the conference and to the speakers, and thank you very much. And conveniently, there's no time for questions, which is good, because I don't want to answer questions about statistics or concurrency.